Chaudry, who's the chief engineer. Has worked on the Intel transactional memory implementation for Java. So seriously, brainy dude. Anyone know what that even is? What? Okay. Exactly. He built it. Most of us don't know what that is. He built it. Okay. And the other gentleman here is Wiqar Chaudry. He is the tech evangelist for NuoDB. This guy designed large-scale marketing databases for banks. And for all of you who aren't clear on what that means, it means all that spam mail you get from Bank of America is through his system. Please welcome Wiqar Chaudry and Sir Thomas. Warmed up. Let me just kind of lay out how tonight's presentation is going to work. I'm going to give everybody sort of a very high-level, 5-minute overview of the company, why the company was started, and then I'm going to hand it over to Trek, and then Trek will take over from there and do his magic, wherever it is that it is. There we go. So, NuoDB is the elastically scalable database. What does that mean? Well, before I can answer what it means, I have to kind of go back in time and kind of share with you guys sort of the great things that our friends at Oracle, Microsoft, and IBM and the likes gave to us back in the 20th century. They gave us a powerful query language, SQL. They gave us industry standards, data guarantees such as ACID. They gave us tools like SQL query tools, client tools. They gave us ETL tools. They helped our employees build up their skills on these data sets and tools that they provided us. And they let us put our existing data someplace where it was structured, safe, and secure. But we're in the 21st century, and what the 20th century databases cannot do is they cannot meet the 21st century challenges that we're all dealing with, right? First and foremost, commodity data centers. So, when we talk about commodity data centers, really the question is, who do you want to buy your hardware from? Do you want to buy it from Best Buy, or do you want to buy it from HP or Dell? Chances are you want to buy it from Best Buy, especially if you're a small company just up and coming. You probably don't have the hundreds of thousands of dollars to stand up a data center. You want to deal with big data. And again, big data means different things to different people. The way that we define big data is really using the 3 V's definition: volume, velocity, and variety. The amount of data that companies are generating these days is unbelievable. And the amount of data that's being consumed by applications such as marketing applications. There's a reason why Google knows everything about you. Their appetite is insatiable. And the speed at which this data is being generated is also incredible. And that's also something that 20th century databases cannot handle very well. Modern workloads, again, that speaks to the big data challenge. 24/7 operations. So somebody mentioned Bend, Oregon, right? That's where all the Google data centers are. Well, there's data centers everywhere in the world, right? Microsoft's data centers are in Japan. Some of their data centers. Lots of data centers are in places like nowhere, Texas. Well, these data centers are distributed all around the world to accommodate the 24/7 workload and operations that we as consumers are demanding because it's noontime somewhere in the world. Geo-distribution, again, just mentioned data centers being distributed all around the world. Traditional 20th century database technologies were not designed to be distributed in that fashion. And then finally, developer empowerment. We built up all these employee skills. We have all these tools that we're used to using. We need to accommodate the 21st century challenges. We need to be able to empower our developers to use the existing skills and tools that they have to solve these 21st century challenges. So in short, there's a crisis in the database world. And we bring up all of these companies here, Amazon, Facebook, Flickr, Wikipedia, Google, not because they're models in terms of solving these challenges, but in the sense that if you take a look at all their different data architectures, they're using very similar technologies, right? They're using MySQL in various different configurations. Some of them are using NoSQL in various different configurations. Some of them are using a combination of MySQL and NoSQL, and many of these companies have actually invented NoSQL technologies to kind of get over this crisis in the database world. And that's a problem, right? So a lot of these companies are doing the same thing, right? They're writing data, they're reading data, they're processing transactions. So why are their architectures so vastly different? Well, there's lots of reasons for that, but you can get into some of those a little bit later. So let me introduce you to a guy. Many of you already know him, obviously from the trivia round. Jim Starkey. He's actually one of the founders of NuoDB. He's also our CTO. Jim Starkey started his career at DEC, as many of you guys may already be familiar with. He invented Firebird, Falcon. He invented the blob data type. He also invented multi-version concurrency control, which is also at the heart of NuoDB in terms of how we manage our data. And Jim had this big idea. His big idea was to build a database on what we call emergent architecture. And emergent architecture is something that exists in nature, right? So the example that we give here is a flock of birds. When a flock of birds takes off, when a flock of birds lands, there's no real leader. There's no master bird that's orchestrating the entire flight process. And we as humans, we also believe, we also behave in the same way, right? So if you think about all the big movements that happen on Facebook and on Twitter, that's also considered emergent behavior, right? There's no leader, from let's say the Occupy Wall Street movement. It's just a bunch of random people that are out there doing crazy things or destroying parks, depending on how kind of what I look at. But our database is built on the idea of emergence. So before we get into the architecture of the database, which Trek will cover, I just wanted to show everybody a couple of slides that prove that our database works, right? So when you add a database to your system, you're able to process a certain number of transactions per second. When you add a second node to our database, your throughput in terms of transactions per second should roughly double. You can go to the next slide. By adding a third machine, again, you should see a significant increase in performance in terms of throughput. And what we're trying to prove here is that we're doing all of this without sort of the traditional administrative hurdles that you have to go through in traditional databases like Oracle or MySQL or the likes. Next slide. And the more nodes that you add, the more scalability that you'll be able to get. And we're not just adding nodes. We're scaling your database, and you're keeping your database across all of these nodes a single cohesive database. There's no sharding or partitioning or anything like that going on. So from an application perspective, when you connect to our database, your application sees a database. It doesn't see the 100 nodes that your database might be distributed on. And we made that very easy for you. We were also able to scale out on infrastructure as a service. What does that mean for you guys? Well, it means that you can spin up nodes on Amazon as needed. So as your demand goes up, you can provision dynamically additional VMs. We also support what we call a heterogeneous deployment infrastructure. So for example, if let's say you're in a tight crunch and you're a startup and your application goes viral overnight and all you have left in terms of processing power are your laptops. So every single employee can give up their laptop, install NuoDB on it, keep your application running through the night until you get funding the next morning, and boom, you can spin up. Right? That's absolutely possible with our database. So without further ado, I don't want to take up too much of your time with my stuff. I want to introduce to you guys Trek Palmer, who is our chief engineer. So once again, this is Jim Starkey's idea, but there's a lot of people that are involved in actually executing his idea. Trek is actually one of those people, and he plays a very integral role in bringing this product to market. Trek?
So as Wiqar said, I am Trent Palmer. I'm the chief engineer at NuoDB, and I'm going to talk about the architecture a little bit. So the agenda, as a nerd, I like lists. So first I'm just going to talk a little bit about myself because, like I said, there was a switch up, so Seth is going to talk, so the web page and things like that. So I'll tell you a little bit about myself in relation to then pay attention to me. The second is an introduction to NuoDB overall, and then I'm going to dive into the architecture, and I'm going to give an example of some unnatural acts that I and probably many people in the room have been forced to perform on normal databases. And it's okay. I was young and I needed the money. And then, God willing, the river don't rise. I'm going to give a quick demo of just starting up the database and show sort of one of the big little additions we made for our latest release, which is this management tool. Show you how easy it is to actually spin things up and down. And then, you know, fear. So, maybe talking, but okay. So, I am a refugee from academia. I was in the PhD program up in Massachusetts, at the University of Massachusetts. I research programming languages and especially transactional memory implementations and semantics. From the huge reaction, my intro, I'm guessing there's not a lot of people who are into software transactional memory in here, but I spent a lot of time working on software. My last professional gig before NuoDB is I worked on the distributed metadata database for the Hitachi data system content platform. It's a clustered appliance, and they have this distributed database that handle all the metadata for terabytes upon terabytes of files that people would ingest into it. So, what is NuoDB? Wiqar said it. It's elastically scalable. Another nice feature of it is multi-tenant. So what that actually means is that you can have lots and lots and lots of databases, right? So we're not talking about having one database that has a half a dozen schemas. We're talking about the ability for the system to provision what we call a domain, basically a pool of hardware resources. And say you've got 1,000 machines. If you need to run 10,000 tiny databases, you can run 10,000 tiny databases and spread them around those 1,000 machines all you want. Or you can run one giant database across those 1,000 machines. And so multi-tenant just refers to that possibility. You tell the system where you want to create your databases, and you add resources to a particular database on a particular net. It is transactionally consistent. So we don't make compromises. So we're not a NoSQL solution, we are a NewSQL solution. And that is buzzwordy, but what it really means is we're actually committed to being transactionally consistent. Your application doesn't, you don't have to reinvent a database every time you use our database, like you would in a NoSQL solution. You don't have to sit there and think about how to make things consistent, how to deal with conflicts, and all of that sort of stuff. So it uses MVCC under the hood to make sure that you can actually interact with it with SQL and get what you expect when you have transactions. And because we're supporting it across lots of hardware, and because we're supporting lots of databases, we also are trying to make it as easy to manage as possible. So that came up when the question was asked, how long does it take to install? And people were throwing out numbers like 90 minutes, perhaps half seriously, but half seriously. And the idea is that it takes almost no time to install it. You throw it on there, you start the little agent, and all of a sudden that hardware is available for running on the thing. Now, if you're running it on an iPad versus a giant piece of metal, maybe you don't want to run so much on it. But it's really easy to set. So Seth Proctor, who's going to give a talk, he's actually off in China, getting married right now, and he informs me that Nuo, which I think is actually pronounced Nuo, but don't call me on that, I'm probably butchering it horribly, is actually Chinese for graceful, specifically in a cloud-like fashion. So graceful like a cloud, and that's the idea, that it's really easy to sort of. Okay, so the architecture from a super high level view is that we effectively have 3 tiers. So the top tier is this management layer, and that's where basically you just sort of add machines to the domain. So that's sort of how you just plant a flag on your hardware resources and say, I want to group all these together, this is going to be my database. And then we have a transaction handling layer. This is a series of transaction engines. These accept client connections, and they talk SQL. And these are the guys who actually handle mutating the data in memory only, and then keeping in sync with each other on all the different nodes. And then there's a storage layer. These storage managers, they sit on the same or different nodes, and they receive the updates from the transaction engines, and they are storing this to durable storage. And again, you can spin up as many storage managers as you want, as many transaction engines as you want. The idea is to be flexible, so that if your application has particular requirements, you can customize your database to your application, rather than what most of us end up having to do, which is spend a lot of time customizing our applications to a particular database. So the agents, this top management layer. So it is just planting a flag on it. That's how you provision hosts for use. So you fire up this little Java guy, and he just sort of advertises himself to everybody else, and just says this machine is available for use in your database. They have this XML messaging system to just talk to one another, and the XML stuff is exposed, so you can do scripting and automation easy with it. We also have this command line management tool in case you need to drive this sort of thing in a more automated fashion, and I'll be showing some of that later. So a broker is a special kind of agent. It has this additional special knowledge, so you have to have at least one per domain. And what it has a sort of global knowledge about the current topology of the system. So as nodes come and go, the broker knows who's what where. And the reason why you want something like this is because clients don't have to know anything about a particular topology. So when a client wants to connect to your database, all it needs to know is where a broker is, and then ask the broker, I want to connect to this particular database, and the broker then redirects it to the nearest transaction engine that can satisfy its requests. So our JDBC client is actually really simple. It's a normal JDBC client with just a little bit of stuff in the front, which is chatting with the broker to figure out how to connect with a particular transaction engine. So the simplified stuff. Okay. So the transaction engines themselves, they're these peer-to-peer in-memory transaction processing units. So they sit in the nodes, they accept client connections, and they have little slices of the data that we call atoms that they're manipulating according to the user's requests. And they're propagating those changes to one another over the network. As I said, the whole thing is using multi-version concurrency control. So you can have consistent views of the data, and you can support a lot of concurrent transactions without anyone stepping on each other's toes. And all of the replication, basically from one transaction to another, is this torrent of background asynchronous messaging that's going on all the time. So we don't have like a normal database where you have this like headache of replication, where you decided where your main database is going to be, and then you have to find where you're going to keep your backup database, and you have to set this giant pipe up and just watch it like a hawk and everything. You spin up a transaction engine, as long as he has those atoms in memory, he's going to be receiving replication messages from everybody else, and everyone's going to be a little bit ahead, a little bit behind of everybody, but consistent all the time. Okay, the storage manager. This is a persistent point for atoms. So they also have copies in memory, and they're receiving updates from all the transaction engines. And then they're in the background continuously writing this stuff to disk. So, well, to a key value backing store. So behind the storage manager is any kind of key value store. At the moment, we're shipping with support for a local file system, which means it's really easy to get going out of the box. You don't have to do anything special. We also support an S3 backend and an HDFS backend. So we don't agonize that much about particular storage on disk or anything. What that means is that if you have any sort of storage solution that looks like a key value store, we can support it. And each individual storage manager is going to have a copy of the entire database, but they're independent of one another. So that gives you a form of redundancy in terms of your durability. Okay, and now I'm going to go through some unnatural acts that I have been forced to do. Okay, so sharding. People like to make fun of sharding. I like to make fun of sharding, so I'm going to make fun of sharding. So an ideal database application, and this is how everyone imagines their application, you just have clients coming in, being driven from some web universe outside, just talking with the database. And that's fine. In databases, all the 20th century database technology that Wiqar was talking about, a big part of that whole design of that system is to just completely dominate and own all the resources on a single node. So as long as you're willing to throw money at a particular node, and as long as your load never exceeds the capacity of a particular node, this is fine. The problem is when you can't, when you have too much load, or you want to have some redundancy. And so one of the standard sort of hacks around this problem is sharding. So it sounds simple. So like, well, we need twice as much capacity, we'll just cut our data in half, and then the application will decide to which half we direct any particular client at any particular time. The problem is it's never that simple. All of a sudden now you have to implement consistency in your application. And even though maybe initially you're just like, oh, we're not going to do that, we're going to just push everything down and make sure everything's fine. After a while, marketing, product management, all those people conspire to ask for features that require all of a sudden consistency across shards, and suddenly it becomes a problem all the time. And it turns out the transaction consistency is very, very hard to get right. That's why implementing databases is painful and difficult, because there's lots of horrible subtleties all the time. And so now all of a sudden, the sharding idea is we're going to take what the database is good at doing and then force application writers to replicate themselves. And that's why sharding is a nightmare. And that's just the beginning, right? Usually, another thing that people ask for is they use global operations, searches and scans, so you end up doing things that look a hell of a lot like joins in your application, or you implement something that looks like a cursor. And then you have to worry about chunking things, and then you have to worry about managing memory because things are just way too big. And all these things just build up. And the funny thing is these are all problems that databases solve, right? But most databases can only run on a single node, and that's like part of the whole problem, right? So people have been solving this problem in ad hoc, cheeseball solutions, and there's no need for that, right? We believe that databases should do what databases are good at doing, which is storing data in a transaction-consistent fashion and letting you look at it. Okay? And of course, the worst one is adding or removing shards, which always comes up and always drives everyone crazy. So when you need to scale shards, well, here's a recipe. This is my experience. So you have to ask your boss for permission. You have to provision the hardware. Then, because there were a lot of subtle bugs you didn't notice, you have to rewrite the application over 6 months and then hope and pray the whole time. People say things like, oh, blah, 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 consistent hashing. That's all true. But no one ever gets it right the first time. And it just becomes a nightmare, right? Everybody knows that. Just sort of like, in order to get sharding right, it expects a degree of perfection on the part of like the database administrators and the application implementers. It's a little unrealistic. Okay. So shards don't scale. Okay. So here's the NuoDB version of shard. So you have what we call a domain. You have 3 hosts in there. Host A, host B, host C, they're each running an agent. One of them is a broker, and you're connected to. Okay? So this is the single node database thing. This is that ideal solution. So you're running a transaction engine to accept client requests, running a storage manager so it makes the changes durable to disk on this machine. And this is analogous to that initial ideal world where someone has provisioned a nice beefy server and they're running their favorite version of whatever database software they want on there. And the application writers just have to write straight SQL and the world is a happy place. But then, of course, those customers show up and they start driving up the demand. And your boss says, boy, they're spending a lot of money. Maybe we should, serve them. And so you have to start adding things to the domain. But in NuoDB, it's really simple. You decide host A is bogged down. So what are you going to do? You're going to go to the management client and you're going to say, I need to add a transaction engine on host B, and why not a storage manager on host B? That way, if host A takes power, everything's still on host B and everything's fine. So now I've got redundancy and scale. Okay? And then, so this is the initial sharding solution. And then they say, well, we need to scale it even more. We need another shard, right? And the old solution that was 6 months and lots of management hell. Now all you do is you just go to the same management thing, exactly the same amount of time. You start a transaction engine on host C and a storage manager on host C. And now you can handle, 50% more stuff. And so NuoDB, adding a shard. I put that in quotes because there's no such thing as sharding in NuoDB. The transaction engines are going to have access to the entire database. If there's, we call them apps, but they're basically like these quanta of data in the database. Whenever a transaction engine needs something it doesn't have in memory, it just asks the nearest storage manager or transaction engine, whichever one happens to have it for a copy, gets it, and then runs with it. When it doesn't need it anymore, it drops it. So it's basically like this massive in-memory cache of database data with a giant SQL processor on the front end. And so you just add more when you need it. Okay? So it literally is as simple as just adding nodes. Okay? And no client had to be alarmed in the making of this distributed database, right? You can keep your application nice and stupid, which means you can get by with nice and stupid application developers, and they're wonderful people. So the brokers are helping you a lot here because they're hiding topology changes. The client software literally has to know nothing about it. They had to connect to NuoDB with a NuoDB JDBC client, the SQL client ahead of time. It's hiding all that from them. All they know is that there's a database named foo or whatever at this domain. They go to it and it connects it to a transaction engine, and they have no idea what host it's running on or anything. They just run with it. And NuoDB is transaction consistent regardless of the number of nodes you're running on. So all the transactional assumptions, and there's going to be a lot of them when you write SQL code, a lot of them you don't know until you do something horrible to yourself, like shard your database, and suddenly you find out that you were depending upon transactional consistency. You don't have to worry about that. NuoDB is just going to keep doing that for you. Okay. So another unnatural thing is eventual consistency. So the way I like to think about it is eventual consistency really is just latent inconsistency. It's just waiting to get bitten after it's too late for you to do anything reasonable about it. So you have to, it's not transactionally consistent, and application porting is non-trivial because you usually have to invert your logic. You have to think about undoing things after they've been done. You have to think about not caring about certain things, compensating actions. And basically what an eventually consistent database is asking you to do is to make a trade-off. It's not unusual. We're engineers, mostly, so trade-offs should be natural to us. But the trade-off they're asking you to make is really icky. It's a trade-off between performance and correctness. Correctness is a really hard thing to trade off. It's really hard to think about it. It's really hard to look at something and say, if this is slightly broken, how bad would that be? Because that's really what correctness trade-offs are. It's just like, what if it gets it wrong sometimes? What does that mean to me? And that's hard to think about. So NuoDB is consistent, transactionally consistent, all the time, everywhere. On every node, we have transactions. We handle thousands upon thousands of simultaneous transactions. Everything's fine. And when a transaction is committed, it's guaranteed consistent. Okay? So the way the commit protocol is going to work is that you specify basically the number of sort of durable places that you want the commit to be registered at before you return it to the user. And so what you're trading off there is performance and availability. So when it's committed, it's guaranteed committed, guaranteed consistent for all time. And all you're just saying is how many storage managers are waiting for to receive this data. And that basically means what kind of availability hit you can take and still survive. So you can decide, basically at commit, like when you're with the commit protocol, you can decide sort of how much you care about a particular transaction. And so you can make trade-offs within the same application between performance and availability. And that's a lot easier of a trade-off to make between performance and correctness.
Can you pick multiple transaction managers or
Well, sure. What do you mean?
Can you pick like multiple transaction managers? Because right now you're picking the storage, like the actual writing to the disk, right?
Yeah.
Can you say you have a lot of transactions and want to run it on 2 transaction managers?
Well, the transactions are going to run on any transaction manager that the client's connected to. So if you have like 3 or 4, if you have 1,000 machines, they're all running transaction engines. They're all going to have, you could potentially have however many clients each one can connect to, and they're all running however many transactions they want to run at the same time. And it's just that when you actually commit, the idea there is in order for it to be durable, so it's an ACID database, so in order for it to be durable for the transaction commit to actually do something, it has to be durable somewhere, right? And so all you're saying is just, I care about it being durable in one place, or I care about it being durable in like 10 places, or however much availability you decide that you need to tolerate. Right. And so that's all you're doing, is you're just specifying different places. Because eventually, so it gets written to one storage manager, but the change is going to get replicated to the other storage managers. So eventually every storage manager is going to have that commit directory. All you're saying is how many do you need guaranteed to have it written to disk before you're willing to return to the disk, or the client. Okay. So that's just a trade-off between performance and availability. You don't have to worry about correctness. When the commit returns, it is actually committed in a normal, old-school database sense.
So if you can't reach to that many storage managers, would it go back from the ones you go to?
Yeah, so that's actually something we're working on right now, is like the specific semantics of those failure cases. So the commit protocol is something that we're like the specifics of which we're working into the current the upcoming release that we're working on. And that's one of those questions that we're having to deal with right now. But the idea is that it would be it would have like a consistent behavior. But yeah, that's one of the possibilities. I'm not going to commit to any particular behavior. Okay, so multi-tenancy is another thing that NuoDB is supporting that is unusual. So traditional databases monopolize a single node. And for a long time, that made a huge amount of sense technologically and economically. Unfortunately, that time has passed. Or fortunately, because I don't work for one of the big database guys, so I'm excited about that. So NuoDB supports many databases in a single pool of machines. So like I said, you have 1,000 machines, you have one giant 1,000 machine database, or you could have 10,000, 100,000 databases scattered around there if you have a use case where you have lots and lots and lots of infrequently used databases, which you really like them to be separated. Okay. And so each database can be scaled as needed independently. So that's the idea where initially you decide they're going to be small, but you figure maybe some of these guys are going to grow and need more resources, and so that you can allocate more resources to them. as they grow, but initially you're not going to expect them. So each NuoDB transaction manager, storage manager is a separate process, and they can only serve one database. So as a consequence, we can support many, many different processes operating on one machine. And that's something we call isolation. So basically, you can have many different databases running on the same machine that are actually independent processes, and there's no way for them to like mess with one another. Okay. So here's a multi-tenancy example. We're back to the 3-host domain. So you've got database A running the transaction engine on host A and storage manager on host B, and the JDBC client just happens to be connected to those two. And then load keeps coming in, so you decide you need to scale this one out a little, and so you add a transaction engine to host C, and now you can have multiple clients connected to multiple nodes, and they're all running the same storage manager. And now you need another database, and not to show any preference, this one's going to be called database 1. And so that one's running the transaction engine on host C, and the storage manager is on host B. So maybe host B is like your entry point to your giant HDFS pool or something like that. That's why you're putting all the storage managers there. And that one's smaller, and it just sits there on those two machines. And this is all one domain, so one management client can take care of 2 databases. And then this one's accepting connections from, say, a SQL client or whatever. And you can keep scaling that. You can keep adding transaction engines and databases however you want across these 3 hosts. You can keep adding, you can add hosts to the domain. And the minute the agent's running and talks to everybody, they'll show up. And then you can start provisioning them. And now, hopefully,
Oh, yeah. So for example, in the 3, you have 3 nodes and each node has a 1 terabyte of storage.
Okay.
So what would be the total storage available for the database? Is it like 1 terabyte?
It is 1 terabyte.
Yeah, but this means that it's not scalable on terms of storage. So for example, if I have 1,000 nodes and each one has 1 terabyte, it means that at the end I have only 1 terabyte that will be over 1,000 nodes, right?
That's correct if you're going to limit yourself to running a local disk. Right? That's why we support those key value stores, because that's sort of the quickest, best solution to support massive storage, is that you can have various storage managers writing to some giant like S-tier or HDFS thing going on. Because we figure the key value guys are going to be working really good at like how do we just pool a bunch of disks together and allow people to read and write named resources to it. And we're just going to focus on how do we do that in a transaction consistent fashion. So this is actually a positive thing. So most databases, so you think of your normal database, it's a giant haul of software sitting on top of the machine, right? Lots of agonizing decisions have been made over the decades about exactly how to wrangle each and every bit and byte when they're storing it on disk, right? Databases have, in some cases, their own like file formats or file system formats that they put on hard drives and things like that. Just outrageous amounts of system engineering has gone into this like one thing. But the problem is you know, basically when you sort of optimize something for the storage layer, you compromise it at other layers, and so all these engineering compromises actually start to pollute the stack and make it much more complicated. And so we've simplified that whole thing, A, because we're a small company, and we're not going to spend a lot of time fucking around on other people's disks. To be frank, it's like, and the other thing is people don't care, right? Like, you have these giant key value stores, people want to write storage however they want, they decided to pool their disks in this fashion versus this fashion, and we're not making you commit to one solution or another. And so we can keep the storage, basically the idea is the format of our object can be optimized for in-memory processing, and then we just worry, you know, get the transaction, or the transaction manager can do its thing as fast as possible, the storage manager has to take it out to whatever key value store it wants.
Okay, so if I have 3 machines and I'm using S3 storage,
yeah.
How, and each machine, for example, the data will be 1 terabyte. So how much data do I have to provision on S3? 3 terabytes? Or
yeah, in that case, it would be possible.
In the transaction, is there a constant polling, or is it just that once the transaction is committed, it's then portioned to the storage managers?
No, so the idea is you're sitting there, so you open a transaction, that just creates a new transaction, right? Everybody finds out about that transaction. That's extremely lightweight process action. And then you perform your operations. We're using multi-version concurrency control, so when you mutate things, they're tagged in a version. That version is known to be associated with a particular transaction. Nothing particularly revolutionary about that. What is revolutionary is that these changes are continuously in the background being asynchronously replicated to everyone who has a copy of this atom in memory. That's what these changes. And then when you actually request a commit, basically what that means is I want to make sure that all the changes I've made that comprise this transaction have been made durable somewhere. Okay. So on the storage managers themselves, they have a process that's writing entire atoms out to the key value store, but they also have what we call the journal, which is in some databases called write-ahead log. So it's basically sort of like logging things like you would in a journaling file system. And so as long as there's a permanent record somewhere in the system of every change that's been made as part of your transaction, then it is in some sense committable. And what the commit protocol that we're working on, and that I'm very excited about, allows you to specify is how many of these storage managers have to agree that that transaction is completely committed in order for you to reliably return to the client. So if you've got a transaction that you don't particularly care about its durability, or like you don't care if because you lose a single machine, you're going to lose the last 5 seconds of store of data or the last 10 minutes of data. Let's say it's user login statistics or whatever. Then you're going to put that at the lowest possible level so that it's as fast as possible. But if you have something like financial data for which you're legally culpable if something horrible goes wrong, you're going to write it out to however many machines your boss and the regulatory agencies require you to, and then you're going to return it. And that's all within the single database. You don't have to do any of this ping-ponging that people do now. It's like, oh, I've got my NoSQL thing for storing all of this like kooky, non-reliable stuff as fast as possible. And then I got my giant, big Oracle box in the corner to do all my financial processing. And I had 2 complete software stacks, 2 completely different sets of DBA priests manning them, and 2 completely different sets of application developers. It's one database that can do both things.
That wasn't quite what I was asking.
Okay, sorry.
But are you familiar with the IBM product MQ series? I think it died, whatever. But it was very transactional. A lot of the financial houses used it, but what it did, it had a constant polling, simplifying. It would say, is there a transaction? And an agent would go back and say, yes, there is. Okay, do it and then commit, and then say that the agent, and then say the transaction was committed.
Oh, okay, so, yeah.
And that's what I was asking when you were saying that yours is more of a passive transaction type thing, or it's only once the transaction is done does your product jump and say.
Well, I mean, it's SQL, so you actually have to, like, if you don't have something like auto commit turned on, right? You actually have to tell the system to commit the transaction, you know, which means you can have jerk users who just sort of start a transaction, mess around with the database, they forget to close it, they go on vacation, and all of a sudden you got some crazy thing eating up resources, like what the hell's going on? Not a problem with NuoDB, of course, like no one will ever do that. But like, you know, basically when you open a transaction, it's just sort of this unending list of operations that are going on, and then at some point you say commit. Now, abstractly, all the commit is just a booking. Say, you know, I would like to know when all this stuff is done. So the way that's implemented is in the semantics in the SQL standard. If anyone is fortunate enough to have read that total, tell you that you're not supposed to return from any sort of committing thing until it is actually committed in some way. And since we are an ACID database, that means it has to be durable somewhere. And it's just a question of how you define durability. And so we define it as any storage manager in the system has a permanent record of everything necessary to comprise that transaction. And we actually, with the commit protocol, will allow users to specify the level of durability.
So you spring into action after the commit?
Well, no. This whole time, you've been asynchronously propagating your changes out there. So let's say you've got a transaction where you're updating 1,000 rows or something like that, right? You read a bunch, you update a bunch, you read a bunch, you update a bunch. As those things are going on, the transaction engine you're connected to is constantly spewing its changes out to everybody else. So the storage manager's been logging this and writing it out to disk this whole time. So the whole idea is you're hiding all this latency by just having everything asynchronously propagated in the background. And then you reach this commit backend. In many cases, it's going to effectively just be a no-op, because when the storage managers have done their job, they tell everybody about it. So then a lot of people know that the transaction is committed before it actually gets to the point where the user commit flows over the wire and it's processed and goes down.
So for example, if you have 100 nodes, and so each transaction has to be reflected on 100 nodes by the end of the day, right?
No. So again, it sort of depends. Ideally, like in the fastest case, all you have to do is have all the changes for one transaction stored on one storage manager, and that's it. Go ahead, because they'll make their way to everybody else. Right. So, and if they make their way from one storage manager to all the other storage managers you've got in the system, that means when transaction nodes start up and pull data from the storage managers, they're going to get the latest transactionally consistent versions. And the minute they pull a copy of that atom into their memory, they're now suddenly going to be a target for receiving the replication messages. So we are consistent everywhere. We're not eventually consistent. We are simultaneously consistent everywhere. So every node knows about all the changes. It's just made locally, so it's a little bit ahead of all its peers. But because those peers have also made changes and those messages are inbound, you're also a little bit behind everybody. But through the magic of multi-version concurrency control, we can manage all this and basically like minimize conflicts to an incredibly low level, and then make it very, very fast.
Plus, isn't it true that if you have 100 nodes, your atoms are not going to exist across every single one of those 100 nodes?
Right, unless you have an extraordinarily popular atom. Right. So the idea is, these things are sort of acting like hashes of atoms. So whatever atoms the clients connected to that individual node need to process their transactions are going to be resident in memory. And if it doesn't need those atoms, they're going to be a background garbage collector going on. They're going to get dropped out of memory. And it's fine, because you can always just fetch them from another transaction engine or some storage manager somewhere. And so basically over time, each individual transaction engine is going to have some partition of the data that's relevant to the transactions that it's processing in a given moment. And through garbage collection and aging of these things, like as the workload changes on the transaction engine, it'll just have them working set in memory at all times. And so part of setting up these things is you can actually specify how you want to provision these guys out. So if you have a small database, you know it's a small database, you can say, I really don't want you to sit in 100 megs or whatever it is. Otherwise, you can just let it fill up memory if you just want it to have like be this big, easy thing.
Yeah, but at a certain point, the 100 nodes will have the same exact copy of the file, the storage file, at a certain point, right? For
No.
consistency, or...
No. They just have to have a consistent view. Right, so I make a change to it, right? That means I'm going to be instantiating a new version. I'm making all these changes. My changes then get propagated to these other nodes. So they made their changes, they're receiving my changes. As my changes come in, it basically is like another secret client changing my memory representation of these things. Now, all these changes are going on in transaction engines. Storage managers don't actually process client requests. They just sit there and passively receive all the transaction engine's messages. And so those flow in. The storage managers are continuously updating their views of these atoms. They're writing the atoms out. They're journaling everything so that the changes are there. And you've got a write-ahead log. You've got a write-ahead. It's just using sort of standard database tricks to sort of make sure that the disk is being written to as fast as possible so that you're getting like low latency and high throughput on commits.
If one of the transaction managers dies, would you be able to cover that transaction?
If it died while a transaction was in flight?
Yes.
No. So the client connects to the transaction engine. The transaction is in some sense local to that transaction engine, even though it's being, the transaction when it's open is registered to all these other guys. The only client that can add operations to that transaction is the one that's connected to that transaction engine. Right? So we're not doing distributed query processing, right? Like the request is not in some sense being spread out across all of these things. So if you're unfortunate enough to be connected to a node that's being hit by a hurricane, just pick some random example out of the air, and your transaction isn't committed at the time that that node is submerged, you're probably going to lose that transaction. But the whole point is, since it's a transactionally consistent database and we're ACID, if you haven't called commit, there's no reason for you to expect any of that to be persisted at all anyways. But it seems like I'm being harsh, but that's the beauty part. Like, people like ACID. I mean, SQL's an ugly, weird language, right? But the semantics are really useful and meaningful, and it's much easier to sort of like, just think about this ugly, weird language and what you want the transactionally consistent view of the world to be, than it is to just sort of like deal with something that kind of writes things whenever it feels like it, and then make your application do all the heavy lifting. Because let me tell you, it's going to be much harder to get it right every time you write the application from scratch than it is to have a database that people are pouring their heart and soul to over years to do it for you.
But on the other hand, if the storage manager dies, you can't recover the transaction and write it to some other.
Well, it depends which storage manager, right? So, like, if you have all these storage managers, if you're processing on the transaction engine, you say commit.
Yeah. It
gets committed to that storage manager, and that storage manager dies before that change is committed to anyone else. Then, as long as that transaction node is still around, everything's fine, because any other storage manager you have in the system is going to pick up that change and run with it, right? The problem you have is we can start having these horrible, catastrophic failures, and that's why we're going to allow in the commit protocol people to specify the number of storage managers, because that's basically you telling the system, like, I'm super paranoid about this data and I need it everywhere, right? So you can have, you have your data center in New York, you've got your 100 transaction nodes, you've got your 10 storage managers, but you're paranoid. So you've got another storage manager that happens to sit in a bunker in Nebraska or Oregon. I don't know where I came up with that idea. And it just receives all these updates and is processing it there. And so only for the big things like the big transactions, the ones where there's money involved, and lawyers, you actually wait until it gets out to Nebraska. But most of the rest of the time, you just sort of trust it to just sort of be your disaster recovery site.
And just to add to that, right? Let's say you get your hands on the marketing database of Bank of America, and you want to manually update your record to unsubscribe to the spam messages that you're getting. You hit update and hit enter on your code client because that's what you're using to connect to the database. Bank of America finds out, they shut that node down quickly. And then they're like, oh, okay, well, this guy, he can't unsubscribe, we need to send him spam. Well, what's going to happen is you're going to find out the client's going to return back some kind of error, and it's going to try to reconnect. And when it tries to reconnect, it's going to say, oh, that node went down. But guess what? I have like 800 other ones that I can connect to, right? So you can just hit submit again, and it'll just, next time you try to hit submit again, it'll connect to a different one.
Right, but I have to click on submit again, right? So it's
Well,
not
you
the
don't,
same transaction.
Well, if you do, I would fire your web developer. I'm going to be honest about this, right?
Right.
Like, if you're going to make like this incredibly direct linkage between the exact actions of the web browser and like the number of times you retry stuff, and that's not going to work for anybody.
Right.
Whenever you have outages. But the model that we're going with here is that because you've got a direct connection to a particular transaction node at the time you establish that connection, if things do disconnect, it's on the application level to basically just retry that. But that's not that unusual. That's what you have to do all the time anyway. So you've got your giant monolithic database, and it dies, right? I don't care what people say about hot standbys and crap like that. There's minutes, right? You know, panic phone calls happen, you know, people run screaming to the bathroom, and like minutes go by, and then finally the backup database is on. You know, those are like the worst 10 minutes of your life, and for 10 minutes it's out there. So applications have to retry. It's just in the nature of things. And so you've got a retrying loop in there. All of a sudden, what works for your giant, takes me 10 minutes to fail over database solution, will work for NuoDB, but the failover will be like that. Well, or, you know, depending upon your network. Yeah.
When you say durably committed to a storage manager, is that to the journal or is that to the file system or the whatever key value store you're using?
Presumably we to whatever was first, right? Whichever wins, right? Because if the entire atom itself happens to be written to disk before the journal's caught up to that particular thing, then that's fine. Otherwise,
so it doesn't go through the journal first?
No, it goes to both places, right? So basically what's going on is the storage manager is got these in-memory copies of these atoms. They're being changed by the messages. And in the background, it's writing them out as these whole things. So like in a normal database, you're kind of doing it like on this page level, block level, or whatever kind of phrase they want to use for like their chunking of the database table. But they've also got some kind of write-ahead log thing because, you know, that's the one that's probably going to get first, right? And so in the current system, I think like the current release is going to be biased towards the archiving, but in the release it should be whichever one's first. Right? It should be fastest.
Does a given atom always reside in memory on some transaction manager?
No. If you're operating on it, yes. In fact, it will reside on the one that you're operating on. But let's say your database goes quiet. You know, you're just a startup, and you know only people in Akron, Ohio care about it. And then when the sun sets and people in Akron are no longer connecting to your website, then everything's just going to dwindle down. Garbage collection is going to kick in, and the amount of memory used on your nodes is going to shrink drastically as the atoms are purged.
So it's not always in memory somewhere for
but when
performance. But how does that caching mechanism work? Like,
well, so if you need something in a transaction, so let's say you're starting with a cold database, right? So you've got your storage managers, and they're backed by however much data. You've got cold storage or cold transaction engines. Someone comes up and they issue a request. There's this thing called the master catalog, which sits on every transaction engine in the storage manager, which basically is exactly what it sounds like. It tells you, it is the master catalog that tells you where any particular atom is. And so the SQL layer's done a really good job of translating god-awful, weird, kind of like English mess that is SQL into a giant operation tree that's being run through the thing, and that actually tells you which particular atoms you need to fetch. It's going to go to the nearest node that has, in the case of a cold database, it's going to be a storage manager. So it's going to go to the guy that's closest to it on the network. Because in the background, there's been this ping going on, where everybody knows who's nearest to it. So you're going to go to the best node, the closest node. And if it's a storage manager, he's going to have to read it off the disk into his memory and then send it to you over the network. Okay? So that's going to be slow.
Yeah.
And the next guy who asks for that is going to get it from you or your storage manager, depending upon who's closest to him, and so on and so on and so on. And so basically, you're going to fill up your memory. And as the working set changes, some atoms are going to get dropped by the garbage collection process, which is going in the background. It's totally concurrent. It's not like don't think of it like garbage collection in the Java sense, right? It's not going to stop the world, pause everybody, figure out who owns what, drop it. It's just going to get it. We spend a lot of time making sure it's not going to stop forward progress on any of the working threads to drop things that are truly cold. It's going to get rid of all those, free up memory for new atoms. So as the working set changes, old guys are going to get retired, new guys are going to come in to fill up that space, and it's just going to churn. And only if you have, only if your working set for all the clients connected to your transaction engine exceeds physical memory do you have problems. But hey, guess what you can do? Start another transaction engine. And then some of the clients will get shuffled over there, and the working set size will shrink back down. And that's the whole point. It's like you see a node that's stressed, you see a node that's in danger, you start another node and take some of its load. And that's the idea behind the whole thing.
How does the JDBC driver know of each of the transaction managers? Or
It
doesn't even need to.
It knows nothing. It's dumb. What it knows is how to talk to a broker. And the broker is wise and all-knowing. And it tells it where the nearest transaction engine is. And so as nodes come into and out of existence, their agents come in and out of existence, and they update the broker as to what's going on. And so then the broker can connect it to it. So all the JDBC driver is it's plain old, vanilla, boring JDBC kind of stuff with just this little thing at the front to connect things. Just point it at a broker. It'll ask the broker, I need to connect to this database. The broker will respond, go to this machine at this port. It'll be your database. And then from that point on, it's very much JDBC driver.
So any of the application code or any client code would
Absolutely.
never have to know of the existence of a or any transaction manager.
Right. All you need to know is, it's the simple sort of normal startup. So if you have a single node database, you got to know where someone is to talk to them. So you have to have a broker or a list of brokers that this application knows about, and then it's just something enhanced its JDBC driver. And if you've written the application well, that's all layered down there into some poor schlub whose whole job is to just make the JDBC thing fine, and you've got all your SQL guys, usually a SQL guy, and then you've got all of your head in the clouds, web designer, UX people doing all their weird stuff on top of that, and they never have to see any of it. And yeah.
Thank you.
So the catalog is actually stored in the broker.
No, the catalogs are actually on the nodes. They're like a special item in the sense that they never get garbage collected because everybody needs it. There's another special one, the transaction manager. Guess why that never gets garbage collected? So you've got the transaction manager and the master catalog. The master catalog tells you where to get everything you want. The transaction manager tells you what the hell's going on. Between the two of them, you're pretty much set. And so everyone has a copy of that. They're actually atoms, though, so they're also being serialized to disk. So the storage manager is making sure that everything's there. And that's sort of how you can restore a lot of your state. Is that as atoms are created, the master catalog is changed, that change is propagated to disk, and now everyone knows about the atom in a very durable way. And so, DDL and DML is this weird kind of thing in the SQL land, but our DDL is basically just DML to these special atoms. We think of it that way. And so they go through the exact same process as everybody else. And so, bootstrapping in the database is a lot, but from our point of view, but none of the users will ever notice it, and it means that there's less sort of craziness to worry about.
And if the broker dies, then your application is pretty much toast. Right?
If your one broker dies, then you have problems.
Oh, so you can have multiple brokers.
Yeah.
Okay.
If you have an existing connection, nobody knew which transaction engine you're talking to, you broke guys, then that time would still continue functioning.
Right, so it is just, like I said, it's just a JDBC driver. There's just a little handshake ahead of time. Once you're connected to that node, if that transaction engine is still up and running and the database to which it's connected is still functional, you haven't had some horrible outage, you haven't lost all your storage managers, it isn't like the last guy running, then yeah, you'll just sit there and you'll never know about the outage because you just established this one connection and it basically persists until you close the connection. And having seen a lot of JDBC code out there, not a lot of people close connections. It's actually a problem. But whatever. So the broker is actually going to redirect you to a node, but then once you're connected, you're connected. Now, that doesn't mean the next person to come in to talk to the broker for that same database is going to get directed to the same node. And that broker goes down, you can connect to another broker, and everything's fine.
So for example, if you have an update query to, let's say, node 1, and then another client connected to node 1000, and it's having a query on the same row that you've just updated. So
sure.
How node number 1000 will know about the update if the storage managers have not yet replicated the changes?
Well, the storage managers aren't responsible for replicating the changes. The storage managers are only responsible for the D in ACID. They're only responsible for writing those changes to durable store. The atomicity, consistency, and isolation is all the transaction managers. So they're actually replicable to each other. So every node replicates to every other node. It's just that storage managers don't accept client connections, so they never make changes locally.
Okay, so the transaction manager on node number 1000 will get a message from node 1 with the update?
If they both have the same atom in memory, yes. So if that slice of the table represented by that atom or set of atoms is in both memories, so it's part of the hot set of whatever random client connections are there, then he will receive that update. They're basically peers. So you can think of it as like a peer-to-peer overlay network for every atom, basically. And so updates will propagate that way. So we leverage MVCC in that way to basically deal with that situation, so that people don't have to do anything god-awful like distributed row locking, or God help you, distributed table locking, or anything like that. All you do is make an update. Guess what? It's a new version. Oh, you delete? Oh, that's weird. That's totally a new version. And so all these things are just new versions on top of that. And so there's just a little bit of a tango that has to happen if you're racing to update the same thing, but it's just a race condition. And we have this notion of chairmanship to solve this in a simple fashion, where basically there's just a fence post and the first person past it wins, and then there's this nice resolution process. In many cases, the update doesn't go away, it just gets a new version number. And then the transaction keeps marching on ahead. And so the whole system is set up so that it uses MVCC, so that you've got node 1, and he's updating, and node 1000 is reading. Well, that's a race, and it's always going to be a race. And it's always been a race in the database world. And so what you can do is you can sort of be draconian about it, lock down the world, and say like, well, this table is owned by node 1, sorry, and then just do that. Or you can just have this multi-version concurrency control, so that basically what that's doing is it's sort of like overlaying a particular view of time on this whole thing, so that if node 1000 in some sort of wall clock sense does a read at the exact same moment that node 1 does the update, it's basically like node 1000 did the read before node 1 did the update. And at that point you're just sort of like ordering operations in time and space, and everything's fine. As long as there's no conflicts, as long as everyone has snapshot consistency, you're good. And that's what MVCC is going to get.
How do you deal with a network partition in that case? Is it just a special case or a different case of the same race?
No, the network partition, so basically you're saying you've got 100 nodes that get sliced into 20 nodes and 80 nodes or something like that. So in a network partition, that's a problem. So we don't want both databases to be going, because the changes made in one partition aren't going to get propagated to the other, and it's extremely unlikely that you're lucky enough that there's no shared atoms between the two. So we basically need to have one partition continue ongoing. And so that's actually something that we're actively working on at the moment. But the idea there would be that the bigger partition would be the winner and would keep on processing requests. The smaller partition would somehow know it's the loser and stop processing client requests and shut itself down until the partition is resolved.
So would the recommendation be to just take drastic measures to make sure that a partition can never happen? Because it doesn't seem like there's a way to deal with that at the application, right?
Yeah, but so it's not so much that a partition never happened, is that you notice a partition and then you fix it. Because as long as that partition is there, your network, you don't have 100 nodes, you have 80 and you have 20, right? And so you can have two NuoDB domains if that's how you want to roll from that moment on. But network partition means that you can't actually use all these resources together. So you need to resolve. But like, let's say that happens. You slice it into 80-20, the 20 dies off, and then the network partition is something awful. There's some backbone New Jersey that just separated your fiber, and like that has to be resolved. And so finally, when that gets resolved, these 20 nodes come back online. Since it's this emergent database, the agents just start back up, and you can start populating them with NuoDB instances all over again. They will join the domain that hasn't seen them in a while. And the storage managers, when they come back online, we have this whole reconciliation process that goes on so that they get all the updates that they missed, so that everybody sees fresh data. The nice thing about it is, unlike an old school database, where if they'd actually been, like one is the replica and one is the source, and they've been separated as a partition, it takes forever because the replica has to get all this data on disk from the source, and that's a bitch and a half. What happens in this case is that the storage managers are doing their reconciliation in the background, but these new transaction nodes are going to be pulling from the other 80 nodes that never had an outage. And so basically your transaction throughput is unaffected. Right? The minute these come back on, you've got transaction engines on them, it's as if they never.
Okay, so at the application level in the partition case, does someone somewhere have to be aware at the application level in order to sort of shut them down? Like if you were to co-locate your application and your database nodes, would you just sort of have to shut the whole thing down, or I imagine you would, right?
Well, I mean, it sort of depends on how you, like, if your application is co-located with the database node, it's co-located with the database node, it's partitioned for us so it's got a similar problem. But those nodes would basically become, like, they would stop processing transactions. And so exactly what would happen would they kill themselves, would they sort of hang themselves in this diagnostic fashion, that's actually not going to work. So I'm not on any particular solution there. But they would somehow know that they're in the losing partition, and they would stop letting you fuck with data.
How do you solve the concurrency problems with assigning a unique transaction ID or sequential transaction ID across these?
You mean two people getting the same version at the same time?
Yes, I'm talking about the MVCC versioning one transaction. I don't know.
Right, so this is the chairmanship. So this is the chairmanship notion, right? Okay, so for a given atom, there's basically a chairman, and all the chairman basically serves as like a fence post. And so the first person past the fence post in that race is going to get that version. So what happens is you sit there and you optimistically grab the next version number and you continue on. Meanwhile, the chairman gets to decide. Because you make this update, it goes out, the chairman sees it, and basically the first person to get to the chairman with that particular sequence number is going to own that sequence number in some sense. However, like, it's not just that the other guy fails. There's lots of different possibilities there to just reconcile things. You can just give the loser a different sequence number and everything's okay. You can just keep on processing, and the guy just has to be able to backpatch the sequence number into his read sets and his write sets, and everything's fine. So that's basically how that's handled. So in cases where you have to have a certain amount of globally consistent state, we have this chairmanship process, but it's basically two things in the entire system.
The chance of role, does that live on a single host other than the manager or that?
No. It's not like there's a chairman host and all the chairmen live on that host. It's just that for any given atom, some node is chosen effectively at random to be chairman for that node. So chairmanship is going to get spread across all of the nodes. As atoms come into and out of existence on them, chairmanship is going to move around and follow the atom sets. And if there's no atom on any transaction node, there's no question about it anyway, so it doesn't really matter. Right? And so that's basically sort of the thing we use there.
Can you tell us a little bit more about the network overhead and the latency required? So exactly if you have multiple sites and you want to have a cluster running across different, like 3 sites, for example, is there a specific latency and throughput that you can calculate relative to the amount of data or transactions? Or
I don't know, like, so in terms of specific numbers, I can't really comment on anything. There's not anything I have like at the top of my head or whatever. But there's no reason why you can't have nodes on the East Coast, nodes on the West Coast. Basically, because everyone's pinging all the time, the nodes on the East Coast are really close to those nodes, they're going to know it. So if you've got a storage, like, you'd be foolish to have nodes on the East Coast and all your storage on the West Coast. But if you have storage on both coasts and transaction processing on both coasts, transactions that come into the East Coast are going to get committed to the East Coast storage manager. More often than not, they are going to make their way over the West Coast. But it doesn't mean they're not going there. They're just going to take a lot longer. And so if all you care about is committing to whatever subset of nodes are on the East Coast, you can commit and just keep on processing, and then the West Coast becomes your disaster recovery area and vice versa. Right? So that's the idea. You have your data center, and then you have just a storage manager hanging out in Nebraska that's just receiving this torrent of replication.
is there a recommendation for the amount of memory and storage that you have to allocate?
Sorry?
Is there a recommendation for the ratio between the memory and the storage and the number
No,
of
you get
nodes?
to tune that however you want. It depends on your application. There's a question about that.
You know what, can we get to the demo because we're going to have more questions.
All right, so on my laptop, I just started off 4 of these agents. It's a 4-node database. This is what we call our console. It's this little web front end to the whole thing. So we've got 4 hosts, 4 brokers, and we can then start a database. So easy to start a database. So we can start a database called movies. Let's say creating a storage manager on this guy. We're giving the storage directory. Temp is a terrible persistent storage directory, but it's great for demos. And now we have a storage manager, and then you can select however many transaction managers you want. So we have 1. And now we need to create a DBA account. We have to go confirming it. Okay, now we've created a database of movies. actually look, and there's movies. And then you can go and drill into it if you want. Unfortunately, the resolution is a little bit low. It's going to show you, here are the two things running. There's a storage manager, there's a transaction engine. Let's see if I can. So now this is just doing something really stupid. It's just creating the schema on this particular database, throwing a lot of crap into it, sleeping for 5 seconds, and then dropping the schema, recreating and throwing things in there. And the whole point behind this is so that I can show you that these graphs are sitting here. It takes every 10 seconds, but they're sort of slowly filling up here. You can see this one filling up. You can also actually drill into an individual node. You can add charts. You can see it rising up here. Oh, check it out. It's 809.
Huh.
Okay. And then you can go back. Okay. And so, this is not exciting. Like, no one wants to watch the transactions running by here, but the whole point is like, I've just created a database and I've started throwing data at it. Okay. And then I come back here. I can see it sort of more generally. If I had more databases, they would show up as well. And then let's say for some reason I've decided that I need more and add a process. I want to add a transaction engine. Let's add another one here. Now I have another transaction engine. And you see it's in real time, more or less real time. It's gathering these statistics from the node. It's telling you how many transactions per second it's going through, and the number of client connections. This is a really dumb client. It's just one. It just bounces around. And so as this thing sleeps, you'll see it transfer to other transaction engines eventually. So as this thing basically disconnects, reconnects, it's going to be bouncing back and forth between the various transactions, and we saw it switch over right there. Now it's running against this guy. And you start a new agent. Let's see, I have a Linux VM here. I'm going to kick off a new agent. Linux comes up. Sell it. Come back here. Go home. Oh, now there's 5 rows. Bing. Nice. And that's seriously how simple it is, right? So you have a machine, you just run the agent on it, and now you can start databases. That's basically the length and breadth of the demo. Wiqar has a much fancier demo. He's sort of more on the marketing side, so he's a lot slicker than my demo. I'm just a poor engineer with a foul mouth, so this is my demo.
In that weren't able to get in before, but then it's getting late, so they'll be around for one-on-one questions. They'll stay as long as you guys want to hang around to ask them. Also, we're giving away these Bose AE2 headphones. We're going to pass around a bucket. Feel free to throw your card in there and potentially win these awesome, totally cool Bose headphones. Bucket's coming around. First question. Question right there.
How many atoms are we typically talking?
How many atoms are you talking about? Well, the atoms are addressed by 2 pairs of 64-bit integers. So that's the mathematical list there. In terms, because you've got these things to be persistent to store, it's however much storage you can sort of accommodate them on. Your transaction engine, the amount of atoms you can have going on at a given time is limited by the amount of memory you're going to give it. And so as you start these transaction engines, you can configure them with an effective cap. And so, if you want to keep them under 200 megs, 2 gigs, 4 gigs, whatever you can. If you've got a big, beefy machine and you'd love to run NuoDB on there, we'd love to talk to you. Also, you can give it a lot of memory.
You can manage the size of the atom.
No, the atoms are chosen, the atoms are basically almost the same size, so they vary a little bit, but they're roughly 50K. And yet they're chosen, again, they're optimized for in-memory performance and in-memory performance. And so a big table is going to have correspondingly more atoms.
So would there be an issue of fragmentation if you've got with thousands of atoms on the file system? I think there are 1 file per atom.
Yeah.
So
Next question? Yes.
Are there any applications like processing big data?
Sorry?
Are there any applications you can use to process big data, like sort of online analytics using it?
Yeah, so from a big data perspective, so again, we define big data as volume, velocity, and variety. Big data is a very ambiguous term. It means different things to different people. So if you are talking about big data in terms of processing millions of transactions per second, you're collecting all kinds of demographic data, or you're running a banking transaction, well, that's part of the way that we handle that is sort of having this in-memory layer and being able to quickly respond to those transactions. So again, if that's what your definition of big data is, that's what we're designing.
I'm more for like reporting purposes.
From an OLAP purpose, or from like
From
an OLAP purpose. So Trek and I have had many conversations about OLTP and OLAP. So part of what we're doing in terms of this emergent architecture, let's say you have short, quick-running transactions from an OLTP perspective. Typically, in an OLAP environment, you're replicating from your OLTP into your OLAP. One of the things that's really cool about NuoDB is because we have all these different nodes, if you're running a long-running query on node 1, right, that doesn't block your OLTP engine from connecting to the other existing transaction engines. So you don't have to do this other separate replication process to handle some crazy messed up query that some analyst has to run because somebody's asking them why somebody didn't pay them, $100 or something like that. So you can continue to process your analytic queries on nodes and let the transaction engines kind of manage the load depending on how you're running it.
And it's MVCC, so you've got some big, crazy, long-running transaction. It's gonna keep all those rows live that it's interested in. You're not gonna have stuff vanish out from under. You're not gonna have to deal with weird consistency issues after the fact. That's why in a lot of cases people replicate their entire thing to some sort of like special purpose analytics thing, so that it's kind of a snapshot. But MVCC gives a snapshot on the fly. Right. So you don't,
So let's say
databases for the pricing.
Right. So let's say you're running your OLTP transactions and you're updating records, right? But at the same time, you're running a long-running query where you need to sort, join, and merge data all together. With MVCC, you don't have to lock the rows that you're querying against, right? So there's no kind of locking issue that you run through traditional old school databases.
Question? Last question of the evening?
Yes.
I think you mentioned you were working on being able to say X number of storage managers need to participate in a transaction. Is it just number, or can you give them like names? Can you say like where? Like you say, I want these two in this DC and this one over here.
Right. So again, that's part of the ongoing sort of thing. Basically, whatever you're specifying is going to translate to a number. And so there's certain things that make sense, right? So one is specifying a subset of them. One might be specifying a majority. So at the moment, the actual mechanism is just going to be specifying a number. So it's, the latest release has some of this technology in it. It's going to be a big part of the GA release. But the specifics of how you, because it's not SQL standard, right? So the specifics of how you specify and what that means or whatever is not yet pinned down. So I can't really say anything specific about that. But, you will be able to support something that translates to a number, right? Where it's between 0 and n, where n is the number of storage members you have.
Okay, both Trek and Wiqar will be here for one-on-one questions. Thank you all for coming.